Hello, esteemed judges and AISC community. I am Angela Fonte, Principal Director of Engineering and Chief Structural Engineer at Ballinger, and I am delighted to present to you the beautiful Fascitelli Center for Advanced Engineering at the University of Rhode Island in South Kingstown, Rhode Island. This is a very special project that I'm proud to call my favorite in my 22 years in the industry. To me, it represents the most collaborative endeavor that I've ever participated in, not only in the integration of architectural and exposed structural engineering, but with the owner, construction manager, steel fabricator, detailer, and erector, and the special inspector. It was a true labor of love and one of those once-in-a-lifetime projects when all facets of the industry came together to lend their expertise to produce a beautiful result. And I'm thrilled to say that it's currently featured on the cover of the current Modern Steel Construction issue. First, to acknowledge the project team, all of whom were key contributors to the success of this project. The owner, of course, the University of Rhode Island. Ballinger was the architect of record, as well as the structural and MEP engineers of record. Our co-structural engineers were O'Day engineers in Providence, who designed the lateral system and the foundations. Construction manager, Dimeo Construction Company, and the steel fabricator, detailer, and erector was all Berlin Steel. And inspections were performed by Briggs Engineering and Testing. The project began as a master plan for the College of Engineering produced by Ballinger and called for the demolition of 5 existing buildings around the engineering quad that were no longer adequate for the advancement of the College of Engineering. And the buildings hatched in red surrounding the engineering quad were all demolished to make way for the literal design of a bridge connecting the basic science campus to the north of the engineering quad to the liberal arts campus and buildings on the south. And the idea was to provide a space through which pedestrian traffic would traverse through the column-free ground floor common space, inviting chance encounters between multiple disciplines and opportunities for interdisciplinary collaboration. As is typically the case for a state project, budget and schedule were tight, and to meet the construction schedule, an early structural steel package was required 3.5 months after the issuance of the design development package. As such, Ballinger's architects and engineers collaborated daily on the design of the bridge, which would highlight exposed structural steel to display engineering insight, and as a nod to the engineering research undertaken within the building. The layout for each of the 3 lab levels would consist of a 160-foot long lab bridge bar of 42-foot by a 160-foot long lab loft spaces for ultimate researcher flexibility, flanked at each end by 2 office wings. So we introduced the columns that you see in blue, and ultimately 3 160-foot clear span trusses 4 stories tall. And this translated into a framing plan for the main lab bridge consisting of 42-foot on center trusses. Each of them cantilever 30 feet at each end beyond the last row of columns, and the north and south trusses also support 6-foot cantilevered corridors along their full length. The main expression of the trusses is clearly in the large X's and diagonal tension numbers that you see on the facade. However, smaller compression props, shown in the slimmer red lines, were implemented at the floor levels to break up the girder spans to allow for manageable structural depth. And because it would be impossible to transport 60-foot tall by 268-foot long trusses to the site, we worked with the construction manager during design to devise the plans for temporary columns, shown here in yellow, that would be installed on their own foundations and used as temporary shoring for the trusses, as it was stick-built in length as long as possible to maximize shop fabrication. To give you an idea of the distribution of forces, you can see here that the top cord supports an unfactored load of 900 kips in compression, with the bottom cord resisting 1,500 kips in tension. The main X numbers provided the main distribution to those cords, with the small end cantilevers supported by the tension diagonal hanger. Now, because the connections would all be exposed behind clear glass curtain walls, we established early on that no gusset plate or bolted connections would be permitted, as they would cast large shadows and cause dark spots on the lit facade. And because our desire to maintain design control over these connections, Ballinger designed engineer, and detailed each and every truss member intersection with the floor level girders. You can see on this framing elevation the callouts at each node. And the result is 3 sheets alone for truss intersection details. Of course, the most critical intersection to understand were the 2 snowflakes that occur in the center of each X where 8 members intersect. So on this detail, you can see that where the highest tension load exists, we maintain continuity in that member as it passes through the floor plane, represented by the top yellow line, and the ceiling is below on the bottom yellow line. So each floor beam and compression member was then spliced through the tension member. Where at all possible, such as at compression-only members, PJP welds were implemented to save not only on weld material, but on the fabrication cost of weld access holes, as each exposed weld was ground smooth and painted, and each access hole and erection bolt opening was filled with weld material, ground and painted, so minimizing holes and weld sizes was a top budget priority. To test the constructability, aesthetics, and intumescent paint application for the snowflakes, Berlin provided an on-site mock-up for testing access to both welds and grinding. The mock-up was left on site for the duration of construction as a workmanship and aesthetic reference. I must also mention the slide bearings that the roller ends of the truss bear on. These are heavy-duty bridge-type pot bearings manufactured by Conserve in Georgetown, South Carolina. Conserve was a tremendous partner in the detailing of these connections throughout design and developed 4 unique bearings to accommodate the actual load levels at each varying condition. And they provided details for our use in the construction documents. A unique situation was presented relative to the deflections of the truss to support curtain wall. And we knew we couldn't simply state in our specifications that the 160-foot truss span would be held to L over 360 and call it a day. So we provided the truss deflection diagrams you see here as part of the construction documents. The exaggerated dashed lines show both the vertical and horizontal truss deflected live load curvature and deflection, with live load deflection values provided in key locations, such as at the center of the truss, where there is both overall truss deflection plus floor girder deflection, or in the upper corners, as shown on the right, where there is both horizontal truss movement and vertical upward deflection due to the cantilevered ends. So the curtain wall manufacturer used these values to design their movement connections and to test the full-scale mock-up in their shop for movement, joints, and leaks. On to construction administration and getting the steel built. Detailing was led by Berlin's brilliant Francis Charbonneau, division manager of Berlin, Canada. 1 week after the steel package was awarded, Berlin Steel's detailer, project manager, and engineer met with Ballinger at the CM's office in Rhode Island to work through a rolling schedule of submissions, splice locations, shipping lengths, and the constructability of the intricate detailing phase to follow. Some pieces were so extensively detailed that it required 3 sheets to detail 1 single member, which could be up to 80 feet long. And given the sheer quantity of connections and welds on each truss member that required special inspections, after the review of each batch of erection details and piece drawings, I would mark up each weld that required inspection with color-coded indications of which type of inspection was required where. So for example, here on this shop piece drawing, welds requiring shop UTs and visual fillet inspections were identified. And similarly on the erection details, I marked up those welds requiring field MP, UT, and visual fillet inspections for the inspector's use, which he relied on heavily. And now on to my favorite part, which is an aspect that we don't present enough about in our industry, which is how to perform under pressure when things don't go exactly as planned. Because of the critical nature of the sequence of erection and the removal of the temporary columns, Ballinger included the sequence of erection on the construction documents. The key shown here is that after all connections were made and the first floor diaphragm tied in, the 15 temporary columns were to be cut. And you can see the yellow painted columns indicating the temporary columns. Prior to the removal of the temporary columns, Ballinger and Berlin met once again on site to review the proposed operation, the order in which the columns were to be cut, and even the anticipated deflection that should be expected with each column removal, so that the erectors could gauge if things were proceeding as designed. The column removal was scheduled for Saturday, April 28th, 2018, with the intent of having no one else working within the building while the cutting operation was underway. Due to some scheduling issues, the column removal was delayed 1 week, and unfortunately, I was scheduled for a short vacation in Toronto that weekend and could not attend. All was going according to plan until about 12:30 in the afternoon that Saturday, when the 5th temporary column in the sequence was cut. As the full cut was made, the column dropped suddenly, the torched gap was closed completely, and the building started to screech loudly. I received 3 rapid-fire voice messages, which I won't play for you here to protect the innocent, but the questions basically posed to me by Berlin's foreman, the superintendent for Dimeo, and the project manager for Dimeo were, are we at danger? Do we need to shut down the job site on Monday? And how soon can you get here? So how do we handle these situations? First, don't run away. Address the situation head on. Be part of the team, like you always have been. And be the voice of reason and gather the facts and stay calm. Gather everything that you can glean from as many different people as observe the situation as you can, so that you can formulate a logical opinion. Communicate with the entire team. Stay close with the CM and the fabricator and erector. Let the architect know what's happening, and absolutely fill in the owner and let them know that you're there helping the situation through. Call in reinforcements. In this case, our friends at LeMessurier in Cambridge had performed a peer review, and due to their proximity to the site, they were willing to come down and help back me up. And of course, get there as soon as possible. So I left my poor husband in an Airbnb in Toronto at 5 a.m. that Monday morning and took a flight to Boston Logan and was on site, I believe, by 7:30 that Monday to meet with the whole team to decide the next steps. It turned out the culprit was a 24-ton delivery of rebar that had been placed directly over the column that had been cut. And the screeching was actually those wood railroad ties which had been set up on top of the shear studs as staging. And as the column deflected downwards when the gap was cut, it sent loud screeches as that railroad tie scraped across the top of the shear studs. So we knew the culprit, and the rebar was moved to another location, but we still wanted to confirm and inspect that everything was still in good condition. And so I walked the site with the inspector and accompanied him as he re-inspected every UT weld on the project. And then finally, prove confidence in your design. All of these steel erectors have families at home, and it's our responsibility to be team members and show confidence in what you've designed and be a team player. And so I stood under there with Scott as we cut the last column. And of course, the end story is success. As that last gap was cut and you could see air on each side, we all breathed a big sigh of relief. And we're extremely satisfied at the end of the day with all we had accomplished together. So the 3 keys to succeeding: quality, know your documents and review your documents 20 times if you need to make sure that everything is in order and that you're issuing a quality set. Communicate, maintain communication during CA, and maintain your integrity, because at the end of the day, as an engineer, that's all you've got. And that's the story of the fantastic Fascitelli Center for Advanced Engineering, a building that truly can't be experienced through photography, so I do hope you all get the opportunity to visit it someday. The project holds a special place in my heart, not only because it exceeded the expectations of the College of Engineering, but because it represents the true spirit of our profession and all that AISC aspires for us to be, in bringing together the best and brightest architects, fabricators, erectors, detailers, manufacturers, painters, and engineers into an inspiring and fulfilling collaboration. Thank you very much for your time and consideration.